All right, hello and welcome back. Today we're going to continue our series on discrete mathematics, and we're actually going to discuss a proof technique today. We're going to talk about induction, which is one of the most powerful proof techniques. Let me take my glasses off. One of the most powerful proof techniques, and something that is just very, very exciting to do. The amount of things you can prove with this is amazing. In fact, just today I was talking to someone and they were just like, I don't believe in induction just because it seems so magical what it can do. So I am very thrilled to be sharing this information with you today. So sit back, relax, listen to the lecture, take some notes, and enjoy. This is an amazing topic. Let's figure out what is induction. So, as I said, it's a proof technique. And as I said, it's powerful, very powerful. And it's commonly used when we see the words for all. So if you're in maybe a mathematical proof class in school, this is maybe just a technique of when you would try to use induction for a proof. Just a little tip, look for the words for all. But perhaps a general form of the problem will be for all integers n greater than or equal to 5, prove that some proposition p of n is true. So this p of n it's intentionally vague in this sense because the p of n could pretty much be anything. And we'll see that there's a lot of different things that p of n can take on, whether that be an algebraic formula or even like a geometric property. It can be used in a ton of places. So we'll explore that momentarily. But the thing I want to focus on is the second bullet point. Induction is very similar to a domino effect. So the idea of induction is if we show for some arbitrary value k that the claim that or the proposition is true, and we show that that would imply that for the value k plus 1, so the value right after k, if we show that that is true because of what k is true, like there is an implication there, then we conclude that it is true for all k that's bounded by the domain. And there are 3 steps to induction, but that's fine. Let me explain this domino effect a little bit more. So I'm going to try to draw some dominoes here. And we'll see what I mean by this in just a moment. My domino drawing skills are pretty bad, I suppose. But here's the idea. So we can just imagine like all of these dominoes standing in a row. Let me just take this and copy it. All right, so we have a bunch of dominoes. And so the key thing is that we're trying to prove something for all. So in the example given, for all integers, that seems like an extremely daunting task, right? If I ask you to prove something for the value of 2, perhaps that's quite easy. You just do something with the value of 2 and you say, hey, this is actually true. If I say prove it for all integers for all positive integers less than 10, well, again, you only have like a couple of values to work with, 1 through 9, so you can just like test those all out and that's fine. But if I just say for all positive integers, in this case n greater than or equal to 5, that's 5, 6, 7, 8, 1 billion, 1 trillion. It never stops. So that's where induction is going to come in handy, where we don't have to be doing casework till the end of time. So let's revisit this domino effect. And we can imagine that these dominoes will go on till infinity. But here's the idea of what induction is. Let's say this very first domino is the smallest value in our domain. So let's say we're working with positive integers, right? We're proving something is true for all positive integers. Then this domino would correspond to the value of 1, because that's the smallest positive integer. So our task with induction is going to be that we want to show that the smallest value is good. The proposition holds for that smallest value. Then what we're going to do is we're just going to take some random domino in the middle, because this goes on till infinity, right? we're just going to take some random domino in the middle. Let me circle that in orange. And we're going to assume that the proposition is true for this domino. And what we want to show is that this orange domino being true causes this green domino to also be true. So there's an implication here. If that's the case, then we can conclude it's true for all positive integers. Because if assuming this to be true makes this one true, then what we can do is we can assume this domino to be true, and then conclude that the one that follows it must also be true. So what we'll see here is no matter which domino we picked, we could have picked this orange one, we could have picked this one, or this one, whatever we assume to be true, as long as we show the next one to be true, it'll cause the dominoes to topple over. So that's why I'm using dominoes. This being true causes this to be true. So we can imagine this domino fall to the ground, and that makes this one fall to the ground, which makes the next one fall to the ground, and so on, and they all fall to the ground. And that's because the first one was true. This causes the second one to be true, which causes the third one to be true, and so on. So that's the visual understanding of what's going on. Hopefully, as I take you through the steps of induction, you'll be able to piece things together into this domino analogy, but with some examples, it'll really start to iron out. So there's three steps to induction. The first is the base case. So here, we're going to ensure that the claim or proposition is true for the smallest value. So if we go back to the domino analogy, that's this thing right here, where we want to show that for the smallest one, the domino that represents the smallest value, we need to make sure it's true. That's the base case. So for example, if we're proving a claim for all natural numbers, our base case should be n equals 0. I guess this really depends on maybe what you're doing, what class you're in. Some classes have natural numbers starting at 0. Some textbooks have them starting at 1. So just be a little weary about this. Let me just put an asterisk next to it. Okay, for positive integers, you would test n equals 1. I think that's pretty unanimous. Negative integers, you do the same. Well, you do n equals -1 and work downward. So I guess in the domino analogy, instead of toppling in the positive direction, see this would be 2, 3, and so on, the dominoes would topple in the negative direction. So that's some guidelines. But another thing to do would be to check if the variable is bounded in the question and adapt the base case accordingly. So if we scroll back a little bit, in this example right here, it does say we're working with all integers, but the key thing to note is that n is bounded. It's greater than or equal to 5. So that means that we want to use that 5 as our base case. So just something to look out for. So that's the base case, first step. What's the second step? That would be the induction hypothesis. So this is when we assume the claim or proposition to be true for some k in our domain. Okay, let's kind of ignore all this at the bottom. Let me just scroll up a little bit. But yeah, what we're going to do is take what we're asked to prove, and we are going to assume it to be true. And for people hearing this for the first time, you're like, this is crazy. How can we just assume something to be true when we want to prove it to be true? Well, that's what induction does. We're going to assume it's true for some k in our domain, and then for good proof writing techniques, you want to bound k appropriately, and it's usually lower bounded by the base case. It could be upper bounded if you're working with negative integers, but usually lower bounded. And then you want to restate the claim in terms of k. Again, these are proof writing techniques, which I highly encourage you to implement in practice. So let's take a look at an example. So the question is to prove for all integers n greater than or equal to 1 that the summation from I equals 1 to n of I equals n times n plus 1 over 2. Some of you may have seen this formula, but that's like saying 1 plus 2 plus 3 plus dot 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 plus n equals n times n plus 1 over 2. Right, that's what we're tasked to prove. So the first thing we'll do is we'll just define this p of n, and we're saying it's a proposition that basically what we're given. Some people like to do that just so we can use p of n throughout the proof instead of rewriting this. Personal preference. So the first step is the base case, and we're working with integers, but the integer value of n is lower bounded by 1, so that's the value in the base case that we want to use. So base case n equals 1. You can compute this left-hand side summation by plugging in a 1 for n, so we get the sum from 1 to 1 of I, that's just equal to 1, and then if you plug in 1 to the right-hand side, you get 1 times 1 plus 1 divided by 2, which is also equal to 1. So the base case checks out. It works for n equals 1. Next is the induction hypothesis. So this is what a standard induction hypothesis would look like. We're going to assume p of n is true when n equals k for some k. This should be greater than or equal to 1. That's my bad. In other words, we're going to assume that the summation from I equals 1 to k of I equals k times k plus 1 divided by 2. There's a lot of things to unpack here. So let's just go through what the induction hypothesis is saying and why each thing is important. So first, we assume p of n is true. So that's going back here, where we assumed some random domino was good. That's the correlation between the two. Okay, assume p of n is true when n equals k. So this, when we're setting n equals to k, that's us choosing a random domino. And it's extremely important to do this change of variables from n to k, because as we work through the next step, if we don't change variables from n to k, there could be a lack of clarity because n is given to us in the question, and if we somehow manipulate n in a way we don't want to during the next step, it can be a little bit messy. So doing this change of variables is really good. For some k greater than or equal to 1, so this 1 comes from the base case, k is lower bounded by it, and we're saying k is greater than or equal to 1. It's greater than or equal to, because remember we're proving all integers greater than or equal to 1. So again, this part here corresponds to us choosing a random domino. And this first part is saying that that random domino, we're going to assume it to be true. And then here, I like to restate what we're assuming just so it's clear for myself and for whoever is reading the proof. So we're assuming this summation equals this right-hand side, and the only difference between this and what we're given is wherever we see an n up here, we've substituted it with the k. So that's the induction hypothesis. It's a small step, but it's very important. So that's step 2. Next is step 3, and you might be like, we haven't even done any math yet. I mean, we did a little bit in the base case, and then in the induction hypothesis, we just assumed something to be true. Where's the math? Well, that's the induction step. So our goal is to show that the proposition is true for the k plus 1 case. Remember, k was our random domino, and we want to show that the next domino happens to be true. We want to show that the toppling occurs. So what I like to do is restate what I wish to prove in terms of k plus 1. So for this example here, I would take the summation, wherever I see an n, replace it with a k plus 1. And that's what I want to prove. And then you're going to manipulate your equality or inequality, whatever you're working with. And usually we manipulate only one side of the equation. Again, just good technique. And then you're going to keep on manipulating until we get something in terms of k. This is slightly confusing because when we substitute k plus 1, everything will be in terms of k, but we want to reduce it to a version of the problem in terms of just the value k. It's hard to explain verbally, so we'll see it in some examples, but the idea is to reduce downwards. Once we get it to this good reduction point, we're going to substitute the induction hypothesis. And you're like, I wonder why it's, oh, sorry. You're like, I wonder why it's in all caps. Well, it's pretty important to do that. That's the whole point of having the induction hypothesis. And, we always have to do this. And for, again, proofwriting tips, always good to cite when and where you're using the induction hypothesis. Not only does it show not only does it help yourself indicate when you're doing a certain step, but usually the substitution can create a huge simplification. So if you don't cite it and someone's reading your proof, they're just going to be like, I have no idea how this person simplified so much. So it's important to cite it. And finally, you're just going to keep on simplifying until you get the equality or whatever. Okay, that's induction. Let's see an example. Let's not see an example. Let's go over some things to remember. So first, these are, again, proofwriting techniques. Clearly define what P of n is before using it. You don't have to use a P of n. Some people like to do it, but it's very important to indicate what P of n is, so that way the reader can, see it in the beginning that, oh, P of n is this. So later on, if they forget what it is, they can just, go back and see it. They don't have to guess. Second, choose the correct base case. This point's kind of silly, or kind of like, well, I mean, obviously, right, if I'm trying to prove something correctly, I gotta do things correctly. But yeah, this just comes down to thinking critically about what your domain is and what things are bounded by, but just a good tip. In your induction hypothesis and step, make sure you change your variable. Usually the problem is given to you in terms of n. I like to switch to k. Can do whatever. But yeah, change of variables is important. I always like to write out what I'm assuming and what I want to show, so it's clear to myself and the reader. And lastly, always use your induction hypothesis in the induction step. Those are my things to remember. Just going forward, I might refer to the induction hypothesis as the IH and induction step as the IS, just some abbreviations. Base case could be abbreviated BC, but I usually don't say BC out loud. All right, now let's see an example. So we want to prove for all positive integers n, let me just scroll up a little bit and zoom in, try to cover up the base case, that this summation from 1 to n of 1 over I times I plus 1 equals n over n plus 1. So before we read the base case, let's just think. We're given n, and we know we're in the positive integers. That's our domain, and it's not bounded by anything else. So we should be thinking, okay, base case, we're working with positive integers. We want to test it for the smallest value in our domain. What's the smallest positive integer I can think of? It's got to be 1. So the base case will test n equals 1 since we're working with positive integers. So the left-hand side, we just substitute n with 1, and we get the sum from 1 to 1 of this fraction, and that just happens to be 1/2. Right-hand side, do the same thing. Where we see an n, we put a 1, and we get 1/2. So there's an equality between the left-hand side and right-hand side, and we're good. We can move on. Just a brief note. What happens if the left-hand side does not equal the right-hand side? Well, depending on your opinion of proofs, you might be really happy or you might be really sad. If the left-hand side doesn't equal the right-hand side, you're done. The proof is over, and you can conclude that the claim is false. Because let's just say the left-hand side didn't equal the right-hand side here. Then we could say that this is not true for all positive integers, because we found a value n equals 1 where the equality doesn't hold. The left-hand side doesn't equal the right-hand side. So if it doesn't hold in the base case, you're done. You can just say that it's not true. But if it is equal, then you have to keep going. All right, let's look at the induction hypothesis. A very short step. Induction hypothesis is usually 1 or 2 lines. So again, this is the question. Let's look at the induction hypothesis. We're going to assume the claim is true for n equals k. So we notice the change of variables. Where k is a positive integer, good, so we're bounding k, like we're specifying the domain of k. And k is greater than or equal to 1, so we have that bound on k. So we're doing a good job. Change of variables, specifying the domain, and providing a bound. That is, so we're going to restate what we're assuming. We assume that the summation from I equals 1 to k, remember we're doing that change of variables, of 1 over I times I plus 1 equals k divided by k plus 1. Good. So change of variables, domain, bounding it, restating what we're assuming. Just some things to remember. Great. Now let's look at the actual math. The induction step. We want to show that the claim is true for the k plus 1 case, the next domino. So we want to prove, and this summation is equivalent to this summation, except wherever we see an n, we put a k plus 1. This n is a k plus 1, same with this n. So the way we're going to do that is we'll start with the left-hand side. What we notice is that this summation can be broken apart. It goes from I equals 1 to k plus 1. So we can break this up into the summation from I equals 1 to k, and then add on the term for when we put in the k plus 1. So, in other words, the summation from I equals 1 to k plus 1 of just something is equal to the summation from I equals 1 to k plus the summation from I equals k plus 1 to k plus 1 of that thingy, right? Just by how summations work, because we're just adding up things, so we're just removing one element and adding it on later. So that's the idea that we'll employ. So we reduce the summation down, so that way it's in terms of just this k here. And then we tack on this term, which is this fraction, but where we see an I, we put a k plus 1. So that's k plus 1 times k plus 1 plus 1. And why did we do this? Why did we break apart like this? Because in the induction hypothesis, we assumed this to be true. The sum from I equals 1 to k of this fraction equals k times k plus 1. And we want to use this in our math. So when we break apart this summation into the sum of these two terms, we see that this right here is what we assumed in the induction hypothesis. So we see here, by the induction hypothesis, we know that this summation equals k over k plus 1. So we'll just substitute that in, right? So this is what we have here, and we'll substitute that k over k plus 1. And here I cited by the induction hypothesis, and now it's just math. This goes k plus 1, this is k plus 2, and then we're going to do a common denominator, so multiply this by k plus 2 over k plus 2, and then multiply this out and combine it with this fraction. We have k squared plus 2k plus 1. The numerator factors into k plus 1 quantity squared, and then we can cancel one of these. We get k plus 1 over k plus 2, and that's equal to the right-hand side. Because here, what we wanted to prove was this, and the right-hand side was this k plus 1 thingy, so that's k plus 1 divided by k plus 2. So we've gotten to the right-hand side. And that concludes the first proof by induction. So what are the key takeaways before we start attacking our own problem? Well, the base case and the induction hypothesis are quite self-explanatory. The key thing about induction is figuring out how you can go from this to a point where we can substitute what we assumed in the induction hypothesis. In this case, it was pretty simple in that we just broke apart the summation just a tiny bit so we could get this term. In other places, it won't be as easy. But this is the most important part about induction, going from this to this. So let's practice. Here's example 2. We're going to prove that 17n cubed plus 103n is divisible by 6 for all natural numbers n. Okay, so I'm going to add some more paper because I know it's going to take quite a bit of space. So step 1 is the base case. So what value do we want to test? Well, we have to look at the domain and if anything is being bounded. So the domain is natural numbers. So, and there's no other bound. So for the sake of this video, we'll just say that the natural numbers start at 0. If you want it to start at 1, that's fine. You can test it, but for this, I'll just say that they start at 0. So we'll test n equals 0. Okay, so what do we want to do? Well, we want to show that this expression is divisible by 6 when n equals 0. So we have 17 times 0 cubed plus 103 times 0. Well, that's just going to be equal to 0 plus 0. That's equal to 0. But more importantly, that's equal to 6 times 0, so it is indeed divisible by 6. It can be a little bit confusing when we have a 0 and how divisibility works, but yes, that is how it works. So the base case checks out. Great, so we can continue. Next is the induction hypothesis. So this is where we have to use our words and say what we're assuming and bound things correctly. So I will write, we're going to assume the claim is true for n equal to k. So we're doing our change of variables because we're given it an n, and now we want to use k, where k is a natural number because that's the domain we're given, and k is greater than or equal to 0. The 0 comes from the base case. This might be a little redundant because the natural numbers are lower bounded by 0, but in my opinion, it's just nice to specify both of these because sometimes in the question we'll say like, prove that this is true for all natural numbers n greater than or equal to 5, and then here we would have to put a 5 here. So it's just practice and it's good. And then I'm going to restate what I'm assuming. That is, and you might be like, why am I restating it? Because here I just said, assume the claim is true. That's not very specific, so I want to be very clear with what I'm assuming. So that is, we assume that 17, now we're going to use k, plus 103k is divisible by 6. Okay? And so another way of saying this is that 17k cubed plus 103k is equal to 6 times some value p for some p in the natural numbers. Right? That's what it means for a number to be divisible by 6. For example, 18 is divisible by 6 because we can write 18 as 6 times 3. So this is sort of like what we'll assume. Cool, so we've done the first 2 steps already of induction, but most of the work occurs in the induction step. So let's write it, induction step. So we're trying to show that the next domino is true. We've assumed it for the k, we want to show it's true for the k plus 1. So again, I like to be a little specific and write out what we're doing. So we wish to show that the k plus 1 case is true. And I'm going to write it out mathematically what we want to show to be true because that just gives me something to look for. So that 17k plus 1 cubed plus 103k plus 1 is equal to, or we'll just say is divisible by 6. Right, that's the goal. We just took what we had here and substituted a k plus 1 for n. All right, well, we're going to work with this, and we want to show it's divisible by 6, and we know at some point we want to use this thing here, where we assumed 17k cubed plus 103k is divisible by 6. We're kind of there, but there's like a lot of things that we have to work out, so let's figure things out. So 17 times k plus 1 cubed plus 103k plus 1. Well, that's equal to 17, and we can multiply that k plus 1 cubed out. I won't do all of the foiling or whatever it's called, Maybe you're familiar with binomial theorem or Pascal's triangle for that. I could do a video on that. That might be fun. And then we can simplify this, or we can just expand it out a little bit more. It's always good to expand things out because then you can narrow in on what you're looking for. And what I mean by narrow in is that actually we can simplify this just a tad bit more, but I don't want to. Like we could combine this 17 and 103, we can combine this 103k and 51k. The reason I don't want to is because I want to narrow in on something that we assumed, right? We assumed that this sum is divisible by 6, and we see that sum right here. So let me just rewrite this. We'll do 17k cubed plus 103k, put those in parentheses, and then the remaining terms can come along, 51k, and then I'll just combine these two constants together into 120, right? And we know that this is divisible by 6 because, well, we assumed it to be divisible by 6. So why don't we use that fact? So let's cite it. By the induction hypothesis, we know that 17k cubed plus 103k is divisible by 6. So we're just going to, we'll just let that equal, like, we'll let this occur. We're going to let 17k cubed plus 103k equals 6p, because that's what it means for it to be divisible by 6. Okay? And the reason we want to do that is because we're still doing like some math, so it's nice to have just like a value to substitute in. Okay, so let's do that substitution. Now we have 6p plus 51k squared plus 51k plus 120. And remember, this is still equal to 17k plus 1 cubed plus 103k plus 1, right? We're still trying to show that this is divisible by 6. And now we're down to here, so we somehow have to show that, like, we can write this as 6 times p, or 6 times some value, because that's what it means for it to be divisible by 6. So how are we going to do this? Well, it's going to require a little bit of, like, some factoring. So we see a couple of terms that are divisible by 6, which is a really good start. So let's take these two and maybe factor out a 6. And these two are quite similar, this 51k squared and 51k. They both share a common 51k. So this is equal to 6p plus 120 plus 51k squared plus 51k. Now we can just factor out something, so this will be 6p plus 20 plus 51k, k plus 1. And we're sort of getting there, right? This is divisible by 6, but this is a little bit weird, right? But okay, let's take a look at this 51. We know that's equal to 3 times 17, so maybe that'll help us a little bit. Times k plus 1. And we're really close to being there. Might not look like it, but this is divisible by 6, or this is 6 times something. If there was a 6 present on the second term, then we could just factor out a 6 from the entire thing and then have this equation be 6 times some massive term, but it doesn't matter what the massive term is because we just want it to be divisible by 6. So we just need a 6 to appear in the second term. We see a 3, that's pretty good. We're almost at 6. Maybe we need a 2 term in there. And we can show that a 2 term can be present because we have k times k plus 1. What can we say about the product of k and k plus 1? Well, let's just put in a random value for k. Let's say we put k equals 3, and k plus 1 is 4. 3 times 4 is 12. Okay, what if we put k equals 7? 7 times 8 is 56. What we'll notice is that this product is always even, because the parity of this k is different from the parity of this k. plus 1. So that means one of these will always be odd while the other one is even, always. So that means this product will be even, because an odd number times an even number is an even number. So we know k times k plus 1 is even. So we'll let k times k plus 1 equal 2m, because that's what it means for a number to be even. It can be written as this form, 2 times m, and we'll specify for some m in the integers, right? Okay, so now when we do this substitution, what we'll see is we still have this 6p plus 20, but now we have 17 times 3 times 2m. And now we can start to see what's going to happen here. This is 6 times p plus 20 plus 17 times 6 times m. And now we can factor out a 6 from both of these terms. 6 times p plus 20 plus 17m. And that's basically the end of the proof. Here we can say, since p is in the natural numbers and m is in the integers, then the quantity p plus 20 plus 17m, that's going to be in the natural numbers. I think m is actually going to be in the natural numbers. I might have to double check that. But regardless, this will be in the natural numbers. So we have shown, what have we shown? Well, we started out with this. And we wanted to show that this was divisible by 6. So we did some simplification. We did a substitution with the induction hypothesis. That gave us this. Did some more substitution or simplification. This, we just noticed something cool that we had, more simplification, and we have it in this form. So this relates to what we were trying to prove. So we have shown that this 17k plus 1 cubed plus 103k plus 1 is divisible by 6. And that is the end of the proof. That's the end of the proof, because we assumed it to be true for some k. We've shown it's true for k plus 1, so it holds for everything, because the k we assumed it to be true for could be literally any value. So that's our first proof by induction. I think we have 2 more, so we'll try to go through those. This is a little bit of a longer video, but it's a very important proof technique, so I just like to spend some time on it. Okay, so here, this is something similar to the first example that we saw, that was written up for us, so hopefully this will be a little bit speedier. So, we're trying to prove this, and unfortunately we're not given a bound on n, but we'll just say, for all positive integers, n greater than or equal to 3. Okay, I guess I just forgot to write it in, but that's all right. Okay, so let's go through it. Base case. So again, you want to look for the domain. Domain is positive integers. Then you want to look for a bound greater than or equal to 3. So the smallest positive integer is 1, but we're trying to prove this for positive integers greater than or equal to 3. So we're going to test n equals 3. Okay, so let's work with the left-hand side. That would be the summation from I equals 1 to 3 of I squared. So that's equal to 1 squared plus 2 squared plus 3 squared. It's equal to 1 plus 4 plus 9. That's equal to 14. Let's do the right-hand side. Where we see an n, we're going to put a 3. So that'll be 3 times 3 plus 1 times 2 times 3 plus 1. All of this divided by 6. 3 times 4 times 7 divided by 6. That would be 84 divided by 6 equals 14. So we have the left-hand side equaling the right-hand side. So we can proceed. Cool. Okay, so now we'll do the induction hypothesis. So we're going to assume the claim is true for n equal to k, so do the change of variables, where k is a positive integer, specify the domain, and k is greater than or equal to 3. So again, we're bounding it here because it's bounded in the question. If we didn't include the bounded this time, then it would be wrong because we're just saying k is a positive integer. We need this bound. And then I'll just restate. So that is, we assume that the sum from I equals 1 to k, and then I'm going to substitute k plus 1, 2k plus 1, all of this divided by 6, or sorry, that should be on the right-hand side. This would be a case, or an I squared. That's what we're going to assume to be true. Okay, now we'll do the induction step. Let me add a piece of paper. Okay, so what are we trying to show? We want to show the k plus 1 case is true. So we want to show that the sum from I equals 1 to k plus 1 of I squared equals k plus 1 times k plus 1 plus 1 times 2 times k plus 1 plus 1, all of this divided by 6. And maybe we can simplify that, but I kind of like to leave it in that form because it might help later. So now it helps to just work with one side of the equation, and typically when we're dealing with summations, it's nicer to work with that side, because as we saw in the first example, we can break apart the summation into the k case and the extra term case. So let me just bring this down a bit here. So we have this summation from I equals 1 to k plus 1 of I squared. That's equal to the summation from I equals 1 to k of I squared plus k plus 1 squared. We're just removing that last term from the summation, but it's still equivalent because we substituted k plus 1 in for I there. So these two are equivalent. And then we assume this to be equal to k times k plus 1 times 2k plus 1 over 6 in the induction hypothesis. So we'll say that this is equal to k times k plus 1 times 2k plus 1, all of this divided by 6, plus k plus 1 squared. And then you might want to cite by the induction hypothesis. Now everything's in terms of k. We've already done our substitution. Now it's just a matter of simplification and hoping and praying that we get this right-hand side. So it requires a little bit of time and effort, but we'll get through it. We're going to do a couple of things at once. So first we'll multiply this. This is k squared plus k times 2k plus 1. All of this divided by 6. And then we'll multiply this out. So k squared plus 2k plus 1. Now I want to combine it into one fraction. So we'll make this a fraction, and we'll do this multiplication at the same time. So if we do the multiplication first, we'll get 2k cubed plus 3k squared plus k divided by 6. And then we multiply the second thing by 6 over 6. 6k squared plus 12k plus 6. All of this divided by 6. And now we'll combine it into one fraction. So this would be 2k cubed plus 9k squared plus 13k plus 6. All of this divided by 6. And I'm kind of speeding through this just because the algebra isn't fun. But remember, this is sort of what we want to get to. So we've combined it into one fraction. Now you might want to try extracting things out. And in fact, if you try factoring the numerator, you'll see that this does equal k plus 1 times k plus 2 times 2k plus 3 over 6. And that's like pretty similar to what we had up here, except we never really simplified this thing up here. So let's try to represent this bottom one as this top one, not the other way around. I like having my final step be in this form because it shows the k plus 1s within the formula. So it shows that substitution. See, if we were to just look at this, it wouldn't be immediately obvious. So we can do that. This k plus 1 is good. That matches this first term up here. K plus 2 is indeed equal to k plus 1 plus 1, so that's good. Let's write that down. K plus 1 plus 1. 2k plus 3, is that equal to this up here? Yes, it is. So 2 times k plus 1 plus 1 divided by 6. And that concludes the proof by induction. You can add some concluding sentence if you want to. I don't really feel like it, but yeah, that's the proof by induction. Let's do one more. I won't actually write it up properly. It'll sort of just be a thought experiment, because this one is more geometric. We're going to prove using induction that the number of diagonals in a polygon with n sides is n times n minus 3 over 2. You may have seen the algebraic proof for this. We're going to do it by induction. So I suppose we should have said for n greater than or equal to 4. Or, yeah, it could be 3, but we'll just say greater than or equal to 4. So base case and induction hypothesis, I'm sure you can handle that. But the induction step is where things get kind of interesting, because we assume that it's true for some k. So in this case, k would represent the number of sides. So let's just draw some sort of polygon here with who knows however many sides, right? And then let's do some different colors. So we have like all of these different diagonals in here, and perhaps there's a lot of them, and we want to show that it's true for like the k plus 1 case. So it would be k plus 1 times k plus 1 minus 3 divided by 2. That's how many diagonals we would want to show it to be true for. The idea behind this proof is that we're going to take, remember, we have to go back to k, because that's something we assumed in the induction hypothesis. So in H, we assumed for k polygon that there's k times k minus 3 over 2 diagonals. Well, how are we supposed to get a k polygon from this? Well, the idea is that we're going to take two of these sides and merge them into one. So we take, let's say, these two sides here, get rid of them, and the diagonals. We're going to add in, or we're going to replace it with one side, and now we have this k polygon. So the k polygon, and that we assume to have k times k minus 3 divided by 2 diagonals. Okay, so we've reached that k polygon state. Now we have to go back to the k plus 1 case, right? We're going to do that substitution, but we're going to do it geometrically. And the way we're going to do it is reintroduce the two sides that we left out. And actually, before I even do this, when we have this k polygon, there's like all of these diagonals, the k times k minus 3 of them, in fact. Right, I think that's most of them. I don't feel like drawing all of them, but you get the point, right? These are all diagonals. Now the thing is, when we go back to the k plus 1 case, those are still diagonals of the polygon. They're still diagonals. We're just missing some diagonals. So the question is, how many diagonals are we missing? Well, we have k plus 1 vertices, right? Because there's k plus 1 sides. And so this is the vertex that we need everything to connect to. So how many things can this connect to? Well, it can't connect to itself, and it can't connect to its neighbors. Well, I mean, it is connected to its neighbors, being this and this, but those aren't diagonals, those are sides. So it can't go to this one or this one. So we would add back in 1, 2, 3, and so on, right? If there were k plus 1 vertices, and we can't connect to 3 of them, that means we add back in k plus 1 minus 3 diagonals. But wait, there's one more that we forgot. And it's this diagonal connecting the two neighbors of the circled vertex. And the reason we have to add that vertex in is you'll notice that this blue line here was the side we created when going to the K polygon. So in the K polygon, this blue diagonal was just a side, which means it wasn't a diagonal in that K polygon. But when we go back to the K plus 1, we have to add this as a diagonal. So we actually add in K plus 1 minus 3 plus 1 diagonals. And that's equal to, let's see, K minus 1 diagonals. And then hopefully, if I did everything correctly, we'll see that K times K minus 3 divided by 2 plus K minus 1, let's see, does this make sense? K squared minus 3K over 2 plus 2K minus 2 over 2. That's equal to K squared minus K minus 2 over 2. That's K minus 2 times K plus 1 over 2. Does that make sense? Yes, it does. Because this right here is equivalent to this. This K plus 1 corresponds to this. K plus 1 minus 3 is equal to K minus 2. So this one I didn't write out formally, but hopefully you got the idea of how something would work geometrically. The idea is still the same. Work from the K plus 1 case, that's where we do all of our work. Reduce it to the K problem. Use the substitution from the induction hypothesis, what you know about the K problem, and then build back up to the K plus 1 case. So it's a similar technique here where we took the summation, we reduced it to the K problem, but we had something else with it. So once we reduced it to the K problem, we did the substitution, and then we built back up until we got to what we wanted. That's the general idea of induction. All right, that's actually the last proof that I had for today. I wasn't keeping an eye on the screen too much, so hopefully my face wasn't covering up most of what I was writing, but it seems to look good. Hopefully this video is educational. This is one of my favorite proof techniques, extremely powerful, and the only way to be comfortable with this is through practice. So I know you've seen me do a lot of proofs. I highly encourage you to just do some proofs on your own so you're comfortable with it. Literally just Google induction proof exercises or something, and I'm sure you'll come across a ton of them. So do that, and you'll be golden. Great proof technique. Hopefully you enjoyed. And yeah, until next time, take care.